Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. People hear a lot about autonomous vehicles, and they often want to know how do these things work? How does an autonomous vehicle actually make the decisions that it makes and drive along a road without human intervention? How does this all work? And so that's part of what the whole Driven show is about, to describe that via certainly our informational episodes and via our conversations. And this episode 19, is about autonomous navigation, meaning how an autonomous vehicle will actually self-drive itself along a road to get to its destination. Like, what is that process? And we've already laid the foundation with an earlier episode on what is a map, what is a mission, and how does an AV, an autonomous vehicle, localize itself or figure out where it is on that map. And armed with that information, where the vehicle is, what kind of map it's allowed to operate in, and what its mission is, and its route to get to the sequence of destinations that it's trying to get to, we can really now talk more intelligently about self-navigation and how a vehicle gets from point A to point B, how it actually gets to its destination. And one of the first things that a vehicle has to do is plan a path. Given a map and given a mission, it may derive a series of waypoints, as we've discussed earlier, along the lane and the lanes in which it's going to operate to get from its current destination to its end destination, or even intermediate checkpoints. But it can't just go from waypoint to waypoint, because those might be rather jagged depending on, of course, the algorithm that generates those waypoints. But very often you're going to be going around curves and through intersections, and you may be even, of course, navigating around objects and obstacles in real time. So you have to plan a smooth path around those curves and through those intersections. And so there's this number of, algorithms, probably a limited subset that are actually used. But one is called spline path planning, which just involves creating a series of spline curves that provide a smooth sort of trajectory for the vehicle to get around those curves, travel around those curves, and travel around obstacles, and travel through intersections. And from that path, you can actually generate a more refined set of waypoints overlaid onto the waypoints that were used perhaps to plan your route during mapping and mission planning and route planning. So these series of more refined waypoints give the smooth path by which the vehicle is going to actually navigate its route. So given that, the fact that you're going to have these series of refined waypoints, at any point in time you're going to have, as we discussed during the AV localization podcast, you're going to have a current position for where the vehicle is on Earth, or in this case on the map on Earth, and on the route in which you're navigating. You're going to know where the vehicle is, and you're going to know at any point in time what your desired next position should be based on your path plan that's overlaid on top of your route plan for navigating to your end destination. So you're going to have a current position, where you are, and a desired position. So where you are and where you want to go at any point in time. And so from that, you're also going to have, based on some of the localization sensing technology that we talked about, you're going to have the current heading of the vehicle. You're going to be knowing, in which direction you're pointed at any point in time. And then you're going to have a desired heading that you can actually compute as the based on your current position and your desired position, your desired next position. From that, you can get, okay, what's my desired heading? Where do I want to go? And there's going to be a difference between your current heading and your desired heading. And that's what we might call the steering error or the heading error. And in this case, that's going to tell you the difference between where you're headed and where you want to go. And so that's your heading error. But you can also consider that your steering error. You actually have to steer the wheel in some capacity over time to that desired heading from your current heading to get to your next projected destination point, right? So now in an autonomous vehicle, you can't just suddenly jerk the steering wheel immediately to that heading because you're going to, drive off the road and it's very erratic. And of course, that's not what we do as human beings either. We don't steer exactly to where we want to go at any sort of discrete instant in time, but we're going to be slowly steering to that position and constantly dynamically changing that, of course, over time. And that's where control algorithms come into play. You're going to actually apply what's called typically a steering PID control algorithm, or some sort of control algorithm, but very often what we call PID, which stands for proportional integral derivative, meaning you take that error and you sort of feed it through a number of simple mathematical equations. One equation is to take that error and say, given this steering error of, say, like 10 degrees to the right, say you need to steer 10 degrees to the right to go from your current heading to your desired heading, and you're going to take some fraction of that. It might be 0.1, it might be 0.2, whatever it is, based on your tuned PID algorithm. You're going to have what's called a proportional constant that's multiplied by that steering error to get what you're actually going to steer to at that current instant in time. So if you have a 10-degree error and you have a steering PID constant, proportional constant of 0.1, you're going to say, okay, I'm going to steer 1 degree to the right because 10 times 0.1 is 1. So I'm going to steer 1 degree to the right at that instant in time because I'm not going to suddenly jerk the steering wheel. Now, if you were to just do that, you would and just have this proportional sort of error applied in what would be a steering P without an I or a D factored in control algorithm, you would have sort of this what we call the drunken sailor type situation, because it's going to oversteer and just you're going to steer back and forth and never quite get to your desired destination. In this case, your desired heading. It's going to constantly change as well, but you're going to constantly overshoot as well each time you do that. So we have another variable or another aspect of this equation called the derivative, which is going to take your change in error over your change in time and maybe with some constant and provide maybe a negative offset for that to kind of keep you more on track to slow your overshoot down as you get to that destination point. In this case, ultimately your desired heading at any point in time. Again, that's going to be dynamically changing, but it's going to help slow down and get you to where you want to be at any point in time. And then there's an integral constant, which is actually taking this sort of your error over time in accumulation type fashion and with some constant and applying an integral term. Now, very often in a lot of the control algorithms that we've seen for steering control, depending on the situation in the vehicle, you might not actually have an integral constant, or you may, but it's certainly it's sort of an art to tune and figure out what these different PID constants need to be to give you a smooth steering control behavior for your vehicle. But suffice it to say, in a nutshell, you have a steering error based on your heading error, and you're going to feed it through this simple control algorithm. What's running, maybe running every 10 milliseconds, every 100 milliseconds, to kind of get your high level sort of steering output that you're going to ultimately communicate to some steering actuator that's actually controlling your steering wheel. And then it itself might have a much higher frequency control algorithm to actually get that steering motor to the desired position that you're commanding it. So there might be multiple levels of PID controls applied. One at sort of the broad autonomy level within, which is looking at the heading error, and then sort of correcting for that and giving you a desired steering command position at a particular control interval every 10 milliseconds, every 100 milliseconds, whatever it may be. And then you're going to have that lower level, more refined position control for the actual motor that's sitting there controlling your steering column or your and the wheels on your vehicle. So PID controls is an important facet of this to give you smooth control of your vehicle once you know that desired heading error. Now, in addition to steering control, you're of course going to have to control the speed of the vehicle. The vehicle is not going to just sit there and steer left and right. The vehicle has to move forward, of course, in the longitudinal direction. And so you're going to have speed control for the vehicle as well. We'll talk a little bit more about that maybe in a future episode, but it's a fairly well understood thing because most everybody has used and leveraged cruise control at one point in their life. And you can set the speed of the vehicle and it's going to ramp up to that speed and hold that speed as you're traveling down the road. And so speed control, of course, is one facet of self-navigation, as is steering control. The steering control is going to keep you on track as the vehicle is moving forward. Now, it's one thing to sort of look ahead and sort of know exactly where you need to go at any point in time, and steer the vehicle accordingly. But depending on how fast you're going, and sort of the nature of the path that you're traveling, if there's curves or if it's a straight road, you're actually not going to. You have to try to figure out how far ahead am I actually looking at any point in time to steer the vehicle. Am I looking, directly in front of me, just a few inches of the vehicle, or am I looking out, 100 feet? Obviously, it's going to be somewhere in between at any point in time, based on your speed and based on where you are and your sort of your path. So there's this concept of path projection, or you might call it path position tracking, where you're going to look out a certain distance ahead of the vehicle based on some heuristic and algorithmic determination. There's one algorithm called pure pursuit, where you're projecting a certain distance out ahead of the vehicle based on your speed, and based on whether that position is actually traversable on the path that you've got planned without going off the road. And so you're going to head for that point. So to give you a more sort of meaningful example here, if you're traveling, say, 25 miles an hour on a straight road, you can be looking directly ahead of you, typically 10 meters. You can be looking out 20 meters. It doesn't really matter as much on a straight road, as long as the road is very straight, because you're going to look for that position ahead of you, and your heading error is going to be fairly small, and you're going to make very small course corrections to just kind of keep the vehicle in the lane and heading towards that pure pursuit projection point ahead of the vehicle. Now, as the vehicle navigates around a curve, if that's not a sharp curve, you might still be looking out 20 meters or 10 meters or so, and not drive off the road, and be turning the wheel in a meaningful fashion based on the heading error to get to that sort of projected point that may be veering to the right or veering to the left a little bit more. Now, as that curve gets tighter, if you're looking out 10, 20 meters, it could be that if you were to just sort of steer towards that point, it might actually start to drive you off the road. So you actually have to kind of pull back on that projected point such that it would be at a position in the middle of the lane such that you're heading for a point that doesn't start to pull you off the road. So there's some dynamic aspect to this sort of moving waypoint, if you will, in front of the vehicle that you're navigating towards, your desired waypoint at any point in time. You can kind of consider it like a carrot on a stick, and that stick is going to lengthen depending on how fast you're going, and it may shorten as well if you're going around a curve that would bring you off the road. So you're going to be looking for this carrot in front of the vehicle, which is your desired position. That's going to change dynamically based on how fast you are and where you are on the road, and how curvy it may be at any point in time. So, in a nutshell, that is self-navigation. So when you look at an autonomous vehicle and you see it doing what seems like magic, there's no one behind the wheel, and the vehicle is turning that steering wheel, staying on the road and turning left and turning right, and of course maintaining its position within the lane. That's really, in a nutshell, how all of this really works in terms of the maintaining the current position of the vehicle in a lane on the road and self-navigating, and of course modulating the speed as well. Now, that doesn't factor in obstacles that you encounter and pedestrians and other vehicles, which is another topic that we'll be discussing in more detail, how it leverages the LiDAR and the radar and the cameras and the other sensors that are on the vehicle to dynamically adapt to what's in front of the vehicle, but without anything in front of the vehicle that it may encounter. That's self-navigation or autonomous navigation in a nutshell. So hope you enjoyed this shorter episode of Driven and informational episode. And there were a few illustrative graphics that you could follow along with in the video form of this. And we'll dive deeper as we go along here and talk about obstacle detection and obstacle avoidance and how that factors into the dynamic change of your path. And of course, the modulation of your speed as you're self-navigating down the road. So see you next time. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web, and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.